Hi, this is Dr. Bricker here with some hints for homework number 4. So the first problem we have is 5.1. 3 ropes in the figure are tied to a small, very light ring, as you can see here. 2 of the ropes are anchored to the wall at right angles, rope 1 and rope 2. And we want to know what are T1 and T2, the tensions here. And we're given this is 30 degrees and 100 newtons. We want to figure out what tension 2 and tension 1 are. Okay, let's take a look at this. Okay, so here's the picture I have. T2, T1, and back over here I'm calling the 100 newtons T3. So this T3 has a part in the x direction, so I'm going to call that T3x. And over here, T3 in the y direction. And we're assuming this ring is not going anywhere, so all the forces have to be balanced. All the horizontal forces have to be balanced. That means whatever's to the left has to be equal to whatever's to the right. And then whatever is up has to be balanced by whatever's down. So T1 to the left has to be equal to T3x. And T2, which is up, has to be balanced by T3 in the y direction. And then I can figure out how much T3x is from the triangle I have here. So, for example, I'll just do this one. I'll leave this T2 to you. But for the T3x, from the picture here, I see that the cosine of 30 is the adjacent side, which is equal to T3x over the hypotenuse, which is T3. So T3 cosine of 30 is T3x. And T3 is, again, 100 newtons. So then you can, once you get T3x, that's equal to T1. So hint, the y direction is going to involve the sine if the x direction involves the cosine. Okay, let's move on to the next one. Okay, 5.3, a 26 kilogram loudspeaker is suspended 3 meters below the ceiling by 2 cables that are 30 degrees from the vertical. And what is the tension in the cables? We definitely need a picture for this one. Okay, so here's what I have. Here's the loudspeaker. I'm just displaying it as a dot here. And forces on the loudspeaker, well, there's the weight of it, mg. And I'm actually given the mass so I can get the weight. And then there's tension here and tension here. This is 30 degrees, this is 30 degrees. So all of the forces have to be balanced. Whatever is up has to be balanced by whatever's down. Whatever's to the right has to be balanced by whatever's to the left. So here's T, there's a Ty. Let me maybe just focus in on this part of it here. If this is T, we have a Ty, and we have a Tx. Same thing over here. This is T. So this T also has a Ty and a Tx. And it's the same angle, so that's the same value of tension. This is T. That's not like T1 or something. So Tx is equal to Tx. Whatever's to the left is equal to whatever's to the right. Just to be complete, and then I can add the weight here. Whatever's up, well, there's a Ty and another Ty. So there's 2 Ty's. Has to be equal to the weight. Okay, so the question is not actually how much is Ty, the question is how much is T. Well, you can get Ty from this. Ty is equal to the weight divided by 2. That's just the y part of it. But if you know the y part of it and you know the angle here, with a little bit of trig, you can figure out what T is. So for example, looking at this triangle, if this is Ty again, the sine of theta is equal to Ty over T. So then you can get T. Draw a little arrow here. T would be equal to Ty divided by the sine of theta. Okay, so get Ty from this, from balancing the forces, and then use a little bit of trigonometry to get T. Again, this is a problem where we are balancing the forces. It's not going anywhere, so whatever's to the right is equal to whatever's to the left. Whatever is up is equal to whatever is down. Okay, let's look at the next one. Okay, in this one, a 6 kilogram bucket of water is being pulled straight up by a string at a constant speed. Okay, so constant speed, going back to the previous chapters, means that the velocity is not changing. There is no acceleration. Okay, so keep that in mind. And let's take a look at this one. Okay, so we definitely get a free body diagram. We've got tension here, weight here, which is equal to mg. So if this thing is going to be moving upward, initially the tension had to be bigger than the weight for that to happen, if it's starting from rest. So this we're seeing is after we've already got it moving. So it's moving, constant speed. If the acceleration is 0, that means the tension must be equal to mg. Okay, so constant speed, no acceleration, those have to be equal to each other. Again, that's once you actually get it going. Part B is now it's accelerating upward. So T, mg. I purposely drew T bigger than mg to emphasize the fact that, well, if the acceleration is up, this one has to be bigger than this one. So then I can say that the net force is ma, and this would be T minus mg. That will give you an actual amount upward, right? There's got to be a net force upward if the acceleration is upward. And then you can solve for T. And Newton's second law is tricky. It seems so easy. Net force is equal to ma. The tricky part is you have to supply whatever's over here. And it really starts with a free body diagram, which I have here. It's just not for fun. It's very useful. And then I can supply the information here. So these force problems, you have to supply what goes in the box. That's what makes them tricky. This is the concept, Newton's second law, and then we can put in the box here what we need. So for example, what are my forces? T up, mg down. This one's bigger than that one, so I'd put T minus mg. Okay, part C is now the acceleration is down. So mg has to be bigger than T for this to happen. And the way I do these, the way I think about it, the minus sign here just means the acceleration is down. So I would put net force, and I'm just looking at the magnitude of the acceleration. ma, so again, the minus sign just means down. I'm thinking about the acceleration is 3 meters per second squared down. So to get something, a value, a net amount down, I'd have to put mg minus t. And then I can solve for t here. So this is, again, the concept. Now we've got to do a little bit of algebra. Move t to the left-hand side, and then move the ma back to the right-hand side. Okay, and the a, again, I'm just using 3 meters per second squared. That's what I would put in here. Okay. All right, excellent. Let's look at the next one. Okay, so 512. A horizontal rope is tied to a 60-kilogram box on frictionless ice. Okay, no friction. What is the tension in the rope if the box is at rest? Okay, so for part A, if it's at rest, it's not moving. There's no force due to friction, so there can't be any force due to the rope. So the tension's got to be 0 for part A. Okay, for part B, what is the tension in the rope if the box moves at a steady 5 meters per second squared? And then part C, what is the tension if the box has a speed of 5 and an acceleration of 5 meters per second squared? So let's sketch this one out. Okay, so for part B, constant speed, again, this thing must have had some tension to get it up to this speed, but now we're just looking at it at a constant speed. Again, that means the acceleration is 0. The only forces that we have are the normal and the weight. There's no friction, say it's moving to the right. There's no friction back to the left, so there doesn't have to be any force to the right. So the tension in this one also is equal to 0. In part C, though, we actually have an acceleration. Again, it doesn't matter what the speed is. If there's an acceleration to the right, like I have drawn it here, there must be a net force to the right. There's no friction to the left. We can have a small, perhaps, tension to the right. So I could use Newton's second law, net force, ma, okay, then you have to supply what goes in the box here, and I'm talking about the horizontal direction, and the only thing that we have is the tension. Okay, good. Okay, so I skipped ahead to number 19, and it takes, in this problem, the elevator in a skyscraper 4 seconds to reach its cruising speed of 10 meters per second. So I guess we're assuming we're starting at rest. a 60 kilogram passenger gets on the ground floor. What is the passenger's apparent weight before the elevator starts moving? And then part B, what is the passenger's apparent weight while the elevator is speeding up? Yeah, we definitely need a free body diagram for this one. Okay, so free body diagram. Before the elevator's actually accelerating upward, normal force, weight. Acceleration is 0. The person's just standing on the scale, perhaps. This one is equal to this one. So by apparent weight, it's saying what is the normal force. So imagine you're standing on a scale. There's a normal force on you from the scale. There's also a normal force on the scale from you. That's what the apparent weight means. What's the normal force? So if you're on a scale, what would the scale actually read? So before you start moving, these are actually equal to each other. So the apparent weight and your actual weight are the same thing in this case. Now, in the second case, when you're accelerating upward, normal weight. So if there's an acceleration upward, I drew the normal force bigger than the weight. Again, apparent weight means how much is the normal force. I can figure out how much the normal force is here. I know what the weight is. This is equal to mg. The normal force is up. I could use Newton's second law. Net force is ma, because again, I'm trying to figure out the normal force. How do I do that? Well, the acceleration's up. What I can use is Newton's second law. Normal force minus mg. So then I have ma plus mg is equal to the normal force. Good, so mg, that's just 60 times 9.8. This is 60 times the acceleration. Well, how can I get the acceleration? Well, I know what I started at. I know what I ended up at. I know the amount of time. I could use kinematics to figure out the acceleration, right, from the first kinematics equation. So velocity final minus velocity initial divided by the time will give me the acceleration. And then I can take this acceleration and put it in here. So if you're on a scale and it's accelerating up, the elevator's accelerating up, the scale actually will read more than your actual weight. And then when you're going at a constant speed, then it's back down to your actual weight. When you slow down, it's less than your actual weight. All right, good. Okay, so 525, we have a 22 kilogram child, goes down a straight slide inclined at 38 degrees, as the picture shows. Okay, the child is acted on by weight, normal force from the slide, and kinetic friction. And we want to know a few things about this. First of all, the correct free body diagram. Okay, good. So we'll actually draw it out and be able to match it up then. And then how large is the normal force of the slide on the child? Okay, yeah, let's draw this out. Okay, let's take a look at this. Here's the incline. Here's theta. I'm just going to represent the child as maybe a box. So the normal force on the child is always perpendicular to the surface. The weight is always straight down. And then we've got some kinetic friction going back the other way. So that's the free body diagram. And then the weight part, as you remember, has a component this way and then a component this way. This one is equal to mg sine theta. This one over here is mg cosine theta. We did this in terms of just g in the previous chapter, if you remember. If g was this way, the one down the incline was g sine theta. I'm looking at the incline like this, x and y. And then the one perpendicular to the motion is this one. Okay, that doesn't look too good. This is supposed to be right here, down the incline. Okay, good. And then we want to know how much is the normal force. Well, the normal force is this way, what I'm calling the y direction. The child's not leaving the incline, so the normal force is this way. It's got to be balanced by a component of the weight, mg cosine theta. Okay, so this answers the question here for part B. Just a little bit more information. this direction, I could say the net force is MA. Why don't I call it the x direction just to really emphasize it? I would have mg sine theta down the incline and kinetic friction back up the incline. I can't really solve this yet because I don't know anything about the acceleration or how much kinetic friction is, but just looking ahead, this is what you could do on the incline part. You don't need it for this problem though. Okay, so the next one we have here, two workers are sliding a 390 kilogram crate, so that's the mass of the crate, across the floor. One worker pushes on the crate with a force of 390 newtons, and the other pulls in the same direction. Okay, so they're both going in the same direction, 320 newtons. Both forces are horizontal, and the crate slides with a constant speed. So again, that tells you that the acceleration is 0 because the speed's constant. What is the crate's coefficient of kinetic friction? Okay, so let's work this one out and sketch the picture. Okay, so here's all the information that I have. The constant speed tells me the acceleration is 0. I'm trying to find mu sub k. Not kinetic friction, the coefficient of kinetic friction. So here's the picture. Normal force, mg, and I've got a couple of forces this way. 390 newtons, maybe I can call that one T1, and the other one's pushing, but I'm just going to call it T also. It doesn't matter if, T2 maybe. It doesn't matter if I'm pushing or pulling. These two forces are this direction. I've got kinetic friction back the other way. And balancing vertical forces, I know that the normal force has to be equal to mg, and because the acceleration is 0, whatever's to the right has to be greater than whatever's to the left. Again, to get this thing moving to begin with, we'd have to have more force to the right than to the left. We're looking at the picture now where we've already got it moving, the acceleration is 0. So T1 plus T2 has to be equal to kinetic friction, right? No acceleration, forces are balanced. Good, so T1 and T2 we know. Put those in. You know how much kinetic friction is. Again, we're asked for the coefficient of kinetic friction. So I'll just put dot, dot, dot. Kinetic friction is equal to some value. And then we could use the definition of kinetic friction. Kinetic friction is the normal force times mu sub k. And in this example, this is just the definition of kinetic friction. In this example, the normal force is equal to mg. Mg times mu sub k. The normal force isn't always equal to mg, just, in this case it is, and it seems like most of the time it is. Now if I were to take this crate and push down on it with some external force, then the normal force would be bigger than mg, but right now it's just equal to mg. Okay, excellent. Okay, so this one, 527, 5,000 kilogram truck is parked on a 7-degree slope. How big is the frictional force on the truck? So I'm not going to do this one in detail, but I will say definitely draw the picture out of an incline, and you can go back to the previous one we did on an incline. Here we've got mg sine theta down the incline, and we have static friction up the incline, and it's not going anywhere, so static friction back up the incline has to be equal to mg sine theta down the incline. So refer back to the problem that we did when we had, I think it was a child sliding down an incline maybe, for the picture. Okay, so let's go on to the next one. Okay, so 535, let me just say a couple of things about this. Review the pages in the chapter concerning terminal velocity. So basically what you have here is the drag force up, and you have mg down. Terminal velocity means that you've reached as fast as you're going to go. The drag force up is equal to mg down. Actually, maybe a little bit of a picture will help for this one. So we're at the point where the drag force is up, and we have mg down. Again, look up the formula for the drag force. These are actually equal to each other. So drag force is equal to mg. And the drag force depends on how fast you're going. So take the formula for drag force, plug it into this in here for d, and then you can solve for that speed. And that speed is called the terminal velocity, as fast as you're going to go. Just one more thing about the drag force. So when you look up the formula, you'll see that it depends on the cross-sectional area that's going through the fluid. In this case, it's air. So this is a bowling ball. The shape is a sphere. So pretend you're looking up and this bowling ball is coming towards you. You know, what is actually cutting through the air? And it's a spherical shape, but it's the cross-sectional area would be a circle. So the area that you need is the area of a circle. So pi d squared over 4, or if you want, you could do it as pi r squared. And then they give you the size of the bowling ball. Okay, good. Okay, so 541, blocks with mass 1, 2, and 3 are lined up in a row on a frictionless table. All three are pushed forward by a force of 13 newtons applied to the 1 kilogram block. Okay, so we'll have to sketch this. How much force does the 2 kilogram block exert on the 3 kilogram block? And how much force does the 2 kilogram block exert on the 1 kilogram block in part B? Okay, so let's sketch this. Okay, so here's our picture of the whole system. Mass 1, mass 2, mass 3. This is 1 kilogram, 2 kilograms, 3 kilograms. And this external force applied to the first block is 13 newtons. There's no friction. And we want to know what's the force of 2 on 3, and also the force of 2 on 1. So if we want the force of 2 on 3, let's look at the forces on 3. So this is the free body diagram for mass 3. I'll call it normal on 3, m3g. Those are equal to each other. And if you just look at mass 3, what gets mass 3 accelerating? Well, it's the force of 2 on 3. So again, this is just the free body diagram of mass 3. And this is what I'm trying to figure out, the force of 2 on 3. There's nothing back the other way on mass 3. Then I could use Newton's second law. Net force, m3 times a. And the only thing, this is the part I have to supply, the only force acting on 3 horizontally is force of 2 on 3. So I can get force of 2 on 3 if I know what the acceleration is. If I look at this as a whole system, so instead of looking at them individually, look at it a whole system, kind of like this. So this is one big mass. So this total mass would be, I'll call it mass of system, would be 6 kilograms, right? 1 plus 2 plus 3. And then I could use Newton's second law for the whole system. Whoops. Net force, mass of system times A. And then as far as the system goes, all I have is normal force for the system, weight of the system, and then I have this 13 Newton force here. On the system, this is what I have. These forces in between 1 and 2 and in between 2 and 3, those are internal forces. Okay, so net force, mass of system times A, and then again you have to supply this part, and the only thing we have is 13 newtons. So I can get the acceleration of the system, which is the same as the acceleration of this one, and this one. So we would have 13 newtons divided by 6 kilograms. And then again, a newton is a kilogram meter per second squared. So we're left with meters per second squared, whatever that turns out to be. 2.17 or something like that. Good, so once you have the acceleration, you can come back here and plug it in, get the force of 2 on 3. Okay, we also want the force of 2 on 1. So let's look at the free body diagram of just 1. I might need a new sheet for this. So the free body diagram for the first mass would be this. Normal 1, m1 times g. We know we got 13 newtons this way. But mass 1 is also in contact with mass 2. So there's a force from 2 on 1 back that direction. So this is just the free body diagram of the first mass. Again, it's a little tricky. They ask what's the force of 2 on 1. When you read through the chapter, there's no force on 2 1 force from 2 on 1 formula anywhere in the chapter. We've got to rely on Newton's second law, and then hopefully what we're being asked for will come out in the wash when we actually use Newton's second law. So net force m1 times A, and then the tricky part is you have to put whatever goes in the box, and I'm referring to the free body diagram, 13 newtons minus force of 2 on 1. And then this is what I'm looking for. It's in a formula. I'll have to do a little bit of algebra to be able to figure that out. But I'll be able to do that. I know the acceleration now, so this thing is just a number. 13 newtons, that's just a number. The only thing I don't know is force from 2 on 1. So let me do the algebra. Force of 2 on 1, I'll put that to the left-hand side. 13 newtons minus MA. And then I can get the force from 2 on 1. In magnitude, it's equal to the force of 1 on 2. That's Newton's third law. They don't ask for that, but I'm just saying if you were going to do the free body diagram of mass 2, you would know how much this force is because it's a third law pair with this one. Okay, excellent. A little tricky, but just keep track of what you're doing and definitely utilize free body diagrams. When you use Newton's second law, think about what you have to actually put here. Okay, and the last one, finally, the figure shows two 1 kilogram blocks connected by a rope. Okay, good. The second rope hangs beneath the lower block. Both ropes have a mass of 250 grams. Okay, so we have to put that into kilograms. The entire assembly is accelerated upward by 3 meters per second squared. And we want to know how much is this outside force F, and then what is the tension at the top of rope 1. Okay, so tension at the top of rope 1. Okay, yeah, let's draw the free body diagram. So here's the picture we saw. Here's mass A and mass B, and they're each 1 kilogram. There's a couple of ropes, rope 1 and rope 2. So not massless ropes, these actually have mass. 0.25 kilograms. The whole thing's accelerated upward at 3 meters per second squared. Okay, so for the first part, to get this force F, let me look at this as a whole system, just like I did before, kind of like this. So I'm looking at this whole thing, and it's got a total mass. So mass of the system would be 1 plus 1 plus 0.25 plus 0.25. So 2.5 kilograms. And then here's the actual outside force that we have going on. Good, so I could use Newton's second law. Net force, mass of the entire system times A. And then I have to supply this part. And on the system, the only outside force I have is this force F. So this is the force that would get all of these components accelerating at 3 meters per second squared. Good, so here's the acceleration, here's the mass, and then put those in, you can get the this outside force. Kilogram meters per second squared, that is a Newton. Okay, and then part B, what is the tension at the top of rope 1? So usually with ropes, we just said it's the tension in the rope. But if I look at rope 1, so let me do the free body diagram of rope 1. Tension, top of 1. And then I'll have the tension at the bottom of 1. And let me use Newton's second law. So this is for rope 1 here. I could say the net force is mass of rope times A. Top tension 1 minus tension bottom 1. Okay, that's what I have here. So what happens if the rope is massless? So let me just say if mass of the rope is equal to 0, then I just, you put this in here, that would be 0. Top of tension 1 is equal to, tension top of 1 is equal to tension bottom one, and then they're equal to each other. But that's not the case here. So if the rope actually has mass, the top tension has to be bigger than the bottom tension to actually give you something, give you M rope times A. That has to give you some value. Now, if the rope is massless, that's when the tensions are the same. Okay, that's the reason why that there's different tension at the top and bottom, because the rope actually has mass. Okay, so now to answer the actual question, what's the tension at the top of one? Well, this is a pretty good free body diagram. It's great, actually, but I don't know the tension at the bottom of one, so that's not helpful to me. Let me do the free body diagram of A. So I got this force here, which I'll know what it is from the first part, and then I've got tension top 1. So tension top 1 on the rope would be up. Tension top 1 acting on A would be down. Those are third law pairs with each other. And then I can get tension top 1 from this picture. Again, this might seem a little weird, but I'm just looking at the forces acting on A. This is the free body diagram for just A. Pretend nothing else exists, just A, and you want to do the free body diagram of just the forces acting on A. So if you think about it like that, just A, you've got the outside force, and then you've got a rope connected to it. Now this tension top 1 is going to depend on mass B, the mass of the weight of this, etc. But we're looking just at the forces on A. And then I can use Newton's second law, net force, mass A times the acceleration, and then I've got to supply this part, F minus tension top 1. And then the only thing that I don't know is tension top 1, right? I know the acceleration and the mass. I've figured out F already. You'll have to do a little bit of algebra. I'll just put this follows that. Tension top 1. From doing the work here, put this over to the left-hand side. This would be F minus mass A times A. Several steps of algebra. Okay, good. Excellent. Any questions, just email me. There's 12 questions. I did most of them, but not all of them. So let me know if you have any questions. Okay.